by the way, hi, Francesco. Our next speaker is also from Germany and also originally from another Mediterranean country, this time Italy.
Yes, exactly. Not far from Susanna, yeah.
Yeah, so our invited speaker, Francesco Piazza from Max Planck Institute for the Physics of Complex Systems in Dresden. He will give us a talk entitled Quantum Nonlinear Optics with a Fermi Surface.
Shall I share the?
I think you can.
Does it work? Yeah.
Yes, we see.
The pointer is visible. Yes.
Yeah.
Very good. Well, thanks a lot to you and all the organizers for putting this together, and Onur especially that they invited me and took care of all the questions I had. So it's really a pleasure to be here in front of this audience. And today I will talk about quantum nonlinear optics. That's the general framework, and in a new, let's say, in a new scenario, in a new setup where we hope could be stronger nonlinearities can be achieved. So, but this is a conference about quantum optics and information, so many of you are familiar with what I will say now, but let me introduce what is quantum nonlinear optics in a slide, like very quickly. So basically, in order to have, in general, nonlinear optics, we have to bring our photons to interact together. And of course, they don't do it at a fundamental level, so one has to use a medium where they can meet and interact with the interactions mediated by the medium. Now, in classical nonlinear optics, it is classical because typically, in order to have the medium affect the photons, you need to modify the medium a lot, which means that you have to put a lot of photons in order to have this back action. And this means that you have scattering not between single photons, but between what I call here photon lamps. So you have a certain lamp of photon or two lamps that you have interact together, and they exit your medium in a correlated fashion. Now, quantum nonlinear optics means moving this scattering from a scattering between lamps to a scattering between single photons. So I have really single photons that enter the medium and correlate and exit again. Now, these interactions between single photons are very challenging to achieve in experiments, but these are, I will tell you, achieved in many experiments. And the trick is basically to increase the cross section for a photon to interact with the excitations of the medium. But if you manage to do this, then this is a very interesting technological resource, essentially, and most of all, because the photons are ideally quantum information carriers. But so if you manage to have them interact, then you can do quantum information processing based on light. So that's of course. That's a very long-term interesting promise. And also you can do all sorts of devices based on single photons, like the full optical version of electronic devices like switches and so on and so forth. So many interesting technological prospects appear if you manage to implement quantum nonlinear optics. And basically quantum nonlinear optics is now quite established in a various type of platforms, and most famously maybe is using atoms or artificial atoms in cavities, in optical cavities. Instead of using strong coupling mediated by cavities, you can use atoms with a strong dipole, which are Rydberg atoms, for instance, Rydberg states. Or you can confine light using evanescent waves, like in photonic crystals, and put atoms close together to generate these nonlinearities. So your medium is generically made of atoms or artificial atoms. But I would claim that basically these classes where quantum nonlinear optics is quite well established, in all these classes, the matter, the medium, is classically correlated. But there is a new set of experiments that is appearing, where the medium which you use to generate this quantum nonlinear optics is made of quantum correlated matter, and in particular fermionic matter. And there are recent experiments where you can have single photons strongly interacting with Landau levels in a semiconductors. You can have excitons, like hybridizing with photons, creating polaritons and then interacting via with a 2D electron gas in recent experiments at ETH, or you can have even single photons interacting potentially strongly with metals or superconductors that can be realized in solid state bulk materials, and also in more synthetic materials made of ultra-cold atom clouds. So all these new platforms that emerge, where basically you can hope to make single photons interact via the excitations of a quantum correlated material. And my question is then the natural one. Our question is, how does quantum nonlinear optics work if my material is quantum correlated, especially as fermionic correlations? And the model to study this, well, before I go to the model, I will say that today I will talk about a specific kind of quantum correlated material, which is simply a metal. So it has a Fermi surface due to the fermionic correlation, and it has Pauli exclusion principle. And let's ask the question about quantum nonlinear optics there. And this is a work done by a PhD in my group, Kieran Fraser, who is now finishing, and also postdoc Bernard Frank, that was at our institute and now moved to the Technical University of Dresden. So the model. The model, for those of you that know quantum nonlinear optics, well, you're typically used to study single photons interacting with the typical quantum emitter, which is a two-level system, right? But instead here, I want to have single photons interact with the motional degree of freedom of quantum degenerate particles. So here I write the second quantized Hamiltonian for some moving particles, can be electrons or can be ultra-cold atoms. Then this is the free part, the kinetic energy, the potential. Then I have my electromagnetic modes with a set of frequency omega mu. And then I have the light matter interaction, which takes this QED type coupling. So I have basically my the density of my matter is coupled to a certain quadrature of my electromagnetic field in a quantized fashion, and I have a set of electromagnetic modes which I label with mode functions eta mu. Now, this is quite a general form, and how can this be realized? And this can be realized in two different, both in synthetic materials like in atomic gases, where you basically use two photon transitions, and you have basically a laser photon that excites off resonantly an internal atomic state, and then the de-excitation is made through a photon that, for instance, belongs to a cavity. And if you go to the dispersive regime for larger tuning, when you can eliminate the internal dynamics of the atoms, then you are left with the motional dynamics of your atoms, and generate this type of coupling here. A similar thing can be done also with electrons in solid state, also using two photon transitions in ways either driving off resonantly using the diamagnetic terms, or either for the excited bands. I don't want to enter this, but basically these are all ways of realizing this QED type coupling. So differently from the standard nonlinear optics, where you use internal degrees of freedom of atoms, here we use the motional degree of freedom of atoms or electrons. And since the motional degree of freedom can be brought by cooling to a degeneracy where the quantum statistics of the particles matter, then the quantum correlations become more and more important, and we shall see what are the effects on quantum nonlinear optics. So maybe before I go on, I should stop. Maybe if somebody is confused by the model, or I completely confuse somebody that this is very unusual for some people, maybe before I go on, I shall ask whether everybody, or not everybody, but at least most of the people are kind of okay with this model and understood the setting. So maybe I want to stop here. Not necessarily for long, but if somebody has a question.
I don't see any question in the chat box, at least. So
either it's great or it's a disaster. But so let me proceed. So the first thing, I see something in the chat, but it's probably not okay. So we want to use this medium of quantum correlated matter to study interactions between photons in this medium. Before we study interactions, we have to study how the photon is dressed by this medium, how the polarization effects work. And basically this is I'm writing here for an homogeneous system of particles, how the polarizability due to this type of coupling I'm used will look like. And this is simply a density response function because my photon couples to the density. And basically, microscopically, the process is that a photon, this wiggle line comes in, removes a particle, let's say in my metal, you would remove it from the Fermi surface, from the Fermi sea, and put it out of the Fermi sea and generate the so-called particle hole excitations. And then the photon leaves the medium again, and is re-emitted by the reabsorption of these particle hole excitations. And this is the diagrammatic representation of this process, where you have the whole line, the particle line, and the incoming and outgoing photon. And this polarizability is known is not an unknown function, and it has the usual behavior. It has a denominator, which is the vanishing at resonance, where the energy of the particle hole excitation corresponds to the frequency of the photon. So this is what one expects. And then it has the balanced nk minus nk plus q, the balance between the let's say in and out processes, basically. And this quantifies the fact that if I have both states occupied, from where I take and I move and I put my particle, this should not have any effect on the polarizability. And this tells you already something about the good regime where to have strong polarization effects, which is the regime of very cold matter, because hot matter has a very broad distribution in momentum. So these two nk and nk plus q by fixed q momentum of the photon will have some overlap if the matter is very thermally broadened, which will decrease the polarizability. If I instead manage to cool the matter and especially reach this quantum degenerate regime where I have either Bose-Einstein or Fermi-Dirac distribution, then this thermal broadening is minimized, and these two distribution functions don't overlap, and I kind of maximize my polarizability. So it's good to have cold matter. And but how this polarizability actually behave? So the polarizability, as I told you, is strongest at resonance, and the polarizability it is a complex function. It has a real part which quantifies basically the change in the the change in the photon dispersion due to the dressing with the excitation of the medium, and it has an imaginary part that quantifies the absorption. So how much is it? The amount to which these processes which conserve energy and momentum lead to the fact that the photon can be absorbed by the medium. And if I take this metal, so I take a medium which has a Fermi surface, a sharp Fermi surface, and I confine it in 1D, which is a thing which you can do both in solid state and these ultra cold atoms. And I take this because it's the most striking regime for this new nonlinear optics. The polarization function looks like that. So for people that know polarization function of emitters, this is very different, and I will compare it later, just in a second. But let me say, first of all, you see that the absorption, which is the imaginary part of chi, it has a box structure. And in particular, you have these windows outside this box where there is no absorption. So, and this is strange, but this happens because my medium is quantum correlated, it's fermionic, it has Pauli blocking. So due to Pauli principle, you cannot have two fermions in the same state. So the photon cannot scatter, photon at a certain energy cannot scatter a fermion into an occupied state. This prevents on-shell processes and so prevents absorption. But still, what is very interesting, I can have still strong dispersion, a strong real part, even where the absorption is zero. Because here you see in 1D, I even have a logarithmic divergence of the real part, so of the polarization, of the modification of the photon dispersion, even though I have no absorption at all. This is very strange. Let's compare it with what you have with standard emitters. If you have a medium of emitters or dipoles, let me I have to click. So then the polarizability looks rather like this. And this is when you have a strong when you want to have a strong polarization, a strong hybridization of the dispersion of photons with the material, you also have a quite appreciable absorption. And this is the problem you have to solve in general if you want to do nonlinear optics, quantum nonlinear optics. And in a medium of emitter, this is solved by the famous trick, which is called electromagnetically induced transparency. basically instead of using two-level system, you use three-level system, you dress them with a laser, and you can generate destructive interference between processes that would lead to absorption, and you can generate a window in frequency very narrow where the absorption goes to zero, and still you see the dispersion is still appreciable, it grows linearly across this zero. And this is the regime where you want to do quantum nonlinear optics with emitters. EIT is really the technique to use to do quantum nonlinear optics with emitters. And I would compare it to what we have in our fermionic quantum nonlinear optics with the Fermi surface, where instead of having a narrow window, which is actually a point, here we have a whole flat window where you have strong, let's say, dispersion and with exactly zero absorption. And so this is a kind of very interesting starting point to do quantum nonlinear optics. And this is really Pauli principle, is the quantum correlation of the medium that do that. So now we determine the polarizability. Now we can look at which kind of collective excitations emerge, the so-called polaritons, where my photons hybridize with the excitations in my medium. And this is the spectrum of this collective excitation, these polaritons. And you see this, you have these two sharp lines. This is a spectrum of the collective excitation. And you have these two sharp lines, which are these polaritons. And these are sharp because outside of this continuum here, which corresponds to this box here, outside of this, as I told you, you have basically no absorption at all. So you can have these very sharp resonances with which are by far not like photons, because their dispersion is very different from the photon dispersion, which will be this parabola here, going up here. So this is very much not a photon, is strongly dressed by the medium, but is absolutely not experiencing absorption at low enough temperature. So this is very good thing. Now I can think to use this to excite these polaritons and have them interact without absorption and do quantum nonlinear optics. And so let me then compute now, imagining sending two photons into my material or into 1D metal and see how strongly they interact. For this, I have to compute another polarizability, which is what opticians call chi3, which is this nonlinearity here. And I can compute this chi3 is a function that depends on 3 frequency and 3 momenta. I'm plotting here this for specific values as a function of the Inca, like this is basically the difference between, this axis is the difference between the ingoing momenta, and this is on the x-axis, the transferred momentum in the scattering. And you see in this color plot, this is the strength of the real part. This is the strength of the actual good coherent nonlinearity that we would have. And you see there is a lot of structure, a lot of large values and small values. So it's good to take a cut. I take this cut here, and I show you as a function of this transferred momentum that this nonlinearity can be very strong, and they can have a lot of resonances, logarithmic, similar to the ones we saw in the polarizability, in the linear polarizability, and also algebraic here, even stronger. So really, we have the potential, due to these almost resonant particle Hall excitations that happen in this vertex here, to have really strong nonlinearities. But that's of course not the full story, because I have also to make sure that my third order, like chi3, doesn't generate further absorption, because this can happen as well. So let me then go to a more concrete, like experimental case, where I send two photons resonant with these polaritons here, so now finite frequency, finite momentum, and I send them with opposite momenta. And now I look at both the imaginary part and the real part of this chi3. So the real part is what I showed you before, that has these strong resonances. And I see, again, due to Pauli principle, there are the windows also in chi3 where there is no absorption at all. So basically this box here, for instance, inside here I have no absorption, but still a very strong algebraic divergence in the coherent nonlinearity. So here, photons or polaritons can interact very strongly, still without experiencing any absorption, both from the linear and from the nonlinear polarizability. So I think that is the working point where one can think to study quantum nonlinear optics with very high, let's say, single photon nonlinearities and basically negligible absorption. So that is basically the main message of this talk. Let me complete this, because if you study scattering between photons, you can study actually the scattering phase shift, and sometimes a good quantification of how you can do, for instance, a quantum gate between two photons is to study the scattering phase shift and the probability to have a pi phase shift without absorption. And here basically you see in this exact region you can have these two, the scattering phase shift to be pi exactly in this region where there is no absorption. So this again is a very good, and you can think about doing really a pi like a photon gate in using this metal in 1D at low temperatures. So this, of course, every idealized. We can have a discussion about how this is corrected, and we'll be very, very interested in hearing opinions about what can be experimentally relevant correction to this. We have, of course, ideas about that. I'm happy to discuss them. And before I proceed, I want to ask how much time I have left, whether I can show a couple of slides more, or I can jump to the end.
We have time.
So do we have time for 2 more slides or so?
Sure.
Okay, so, well, because now I told you about single photons, a pair of photons interacting in this medium with strong nonlinearities. Now I want to show that actually there's another interesting nonlinear effect that you can have here, where even the formation of polaritons itself can become nonlinear. And this happens because, again, in this, due to the fact that you have the Fermi surface, as I showed you in this plot, there is this particle continuum that has this form in this is true in 1D, and you see that the particle continuum here touches 0 frequency. So actually, at when my photon momentum Q is equal to 2 times the Fermi momentum, which is the size of the Fermi line, let's say, of this metal, then I have gapless excitations around at finite momentum, which is a simple thing. If you have a Fermi surface, a Fermi C here, and the photon has the right momentum, you can transfer a particle from one side to the other of the Fermi surface, which costs no energy, and still transfers a finite momentum. And this is known in solid state like the Polarization instability, but basically it means that my system actually, if you couple it to photons which have momentum 2kF, or at least some of the photons have this momentum, my metal will become unstable and become an insulator and gap out the Fermi surface. So if the Fermi C is gapped out, so basically there is no more gapless excitations. And this is done by forming a spatial pattern in my material, which is dimerized. Basically, it has the right period to gap out the Fermi surface, and basically my system chooses one of 2 possible dimerizations. Basically, it gets this modulation by breaking a discrete symmetry, like which is inherent in the system. And now I want to study how the excitations in this dimerized phase work, in this dimerized insulator. And you have 2 types of excitations. You have the standard polariton, if you want, where you have a photon comes in and as an energy that can overcome the gap and excite again a particle or excitation. So this is basically similar to what we analyzed before. So I just excite really a particle in its own lattice. But there is a lower energy excitations that a photon can induce, which is basically an excitation that involves also the deformation of this lattice. So basically, my system prefers to deform the lattice and create a bound state here, which is in the middle of the gap. And so the particle is excited into this bound state, which corresponds to this deformation of the lattice. So this is cost actually much less energy than the normal, let's say, polariton. And this is actually basically where the photon is interacting with, instead of a simple particle excitation, is interacting with or hybridizing with a domain wall. And this is basically an intrinsically nonlinear type of polariton. And this is actually very interesting because it's basically a topological polariton. Because to remove this domain wall, you will need to globally change your, modify your lattice. So there's nothing local that can remove this. So this is very interesting because if I can store my photonic excitation in such a topological excitation, so I make my polariton and in principle the quantum information that I might store in my photon, that is contained in my photon, I can store it in a topologically protected excitation. So it would be interesting to investigate how this can be used for quantum information storage. And this is basically analog to the excitations that you have in these known SSH models for polyacetylene, for instance, where you have these dimerized patterns and you can excite these solitons. But now instead of having phonons, like in polyacetylene, we have photons here. And for quantum information, the photon is surely the better collective, the better excitations with respect to the phonon. So as I said, this might be interesting for applications of this type. So with this, I should stop, and thanks for the attention, and hope for some questions. Thanks.
Thank you very much. Thanks, Francesco. Any questions? We have a question from Onur Umurcalılar. You can also read if you want. Is your model suitable to be coupled with schemes that produce artificial gauge fields, for example, to get to the fractional quantum Hall effect regime?
Yes, this is something which is actually on our list, because instead of coupling, I should go to basically our list of things, and there is this thing of coupled to other electronic phases like superconductor and magnets, and this is actually these experiments that I showed you in the beginning is actually Jerome Feist at ETH also, and this experiment here, basically, where now I jump ahead. They basically, instead of having a photon exciting a metal, they have photon coupled to Landau levels. Basically, the photon is coupling to different, is driving the excitations between two different Landau levels. And in principle, this can be, Jerome Feist can study both the integer and the fractional quantum Hall, and you can study the corresponding polaritons like that are formed, and even quantum linear optics. And he has, even the interesting thing is that the coupling between matter and light in this Jerome Feist system using these split ring cavities are called in these monolayer materials. This is huge. It's in what is called the deep strong coupling regime, where the coupling is even larger than the characteristic photon frequency. So it's really huge coupling. So it's very promising. He studied already the effect of this on how the quantum Hall effect is modified by hybridizing with photons, and it's very interesting new direction.
So do you see the question from Sevinçli? What is the order of magnitude of Chi3 comparing the other nonlinear medium?
Oh, this I don't know, because I have no numbers now in my mind. Compared to other nonlinear media, I cannot tell it on top of my mind. I should look into our calculation and look into other nonlinear media. But I think more than the actual absolute number, I think the quantification of how good your nonlinearity is to do, for instance, like a quantum gate between two photons, is to look at the phase shift. Because if I can do a pi phase shift without absorption robustly, then I have the necessary nonlinearity that I need, I think, at least for that. So I would, instead of quantifying how large Chi3 is, I would ask myself, what is the device that you want to build and which Chi3 do you need? But I agree with you that it would be interesting to put numbers and compare, and this I'm not able to do now, sorry.
Thanks. Let's move to Barış Malcıoğlu. Any suggestions for systems that can topologically protect these states? To be more specific, do you see any potential in 2D correlated materials that are quite popular nowadays in the space?
Yes, we are studying. I mean, I mentioned now this quantum Hall bars coupled to strongly to single photons. And there are also at ETH, there is a Tachimamogu as, for instance, these transition metal dichalcogenides coupled to photons. And these are all interesting sources of quantum nonlinear optics. Actually, we are studying this also in this paper. I didn't have the time to mention. We are studying optical nonlinearities in transition metal dichalcogenides, so these 2D materials. And these are also interesting for generating not only nonlinear optics, but also coherent light sources of all sorts, because the excitons are really tightly bound. Regarding topology, the only topology we studied personally is this 1D SSH type of topological polaritons, but we just scratched the surface, because now we can study, as you mentioned, all sorts of 2D materials with topological band structure and see how they hybridize, how they address photons, and with or without magnetic fields. And so I surely envision a lot of interesting things to look at. Yeah.
Okay, thank you. two more questions, one from Levent, and then Emre Yüce will ask himself, I think. Levent Subaşı asks, can you comment on the relevant temperature scales?
Yes.
Is called referring to Fermi temperature.
Yes, that's absolutely relevant. Let me pick one slide, let's say this one here. So, because for instance, you will say, look at the optical nonlinearity, the real part, so the good coherent nonlinearity is large here, let's say here or here, and this box is perfect, so I have no absorption, but it's perfect only at t equals 0, like t much smaller than tf. So you should ask, how large can the temperature be in order for this effect to survive with respect to the Fermi temperature? And the thing is very robust, because this is, if you increase the temperature, this box is not that immediately becomes smeared out, but it has only a small exponential tail, which is basically decaying like t over tf. So basically, in cryogenics or in ultra-cold atoms as well, you can have really a temperature which is like 0.1 TF, and in solid state even much less. And so I think this is very robust with respect to temperature, because this is only an exponential correction, and so it's not that you get a large tail immediately. I think what is more relevant, especially in low dimension, is the robustness against interactions between your electrons or the particles, because if you add interactions to a metal in 1D, you get a Luttinger liquid. And these has a completely different spectrum of excitation. They are not your normal particle excitations. And so we are studying this now, how robust it becomes if you add interactions. And so yes, but that's the relevant question, and it's a good news with respect to temperature for sure.
Thank you. So let's pass to Emre.
Yeah, thank you very much for the presentation. My question is about the relation between the real and imaginary parts of Chi3. So we know that via Kramers-Kronig relations, they are related in linear regime, of course. So how about in Chi3? Don't we expect such a relation also?
Of course, yeah, it's just more complicated, I would say, because the frequency dependence is more complicated. So, yeah, you're absolutely right. The Kramers-Kronig relation always exists because those are always retarded response function, and so they have the poles on only one side, and so you can always write a Kramers-Kronig relation. We didn't use it to compute it, but we compute them both separately. But we could have just computed the real part and then obtained the imaginary part from it, or vice versa. So I can tell you that the Kramers-Kronig relation are respected in our Chi3. Because we computed it correctly, otherwise it would be wrong. But I don't so. Or are you asking, can I use the Kramers-Kronig relation?
Region, if you look at the in-box region, I
mean,
if one of them is constant, the imaginary part, whereas the real part is changing. So
yes,
this I wouldn't expect actually. That's why I'm raising my question.
Absolutely, because if you take a constant imaginary part, you use Kramers-Kronig, you get an algebraic divergence, and this is what at the edge of this box, and this is what we get. So this is really, you could have guessed by Kramers-Kronig. Yeah, this is what you said. Here is more complicated. You have a lot of features, because if you zoom into the real part, it actually does a lot of things here. It has log divergences, it has algebraic divergences, and it all depends on how many resonant processes you can get into these lines here, like how many resonant particle excitation you can create. So it's a very rich structure, and it depends on 3 frequencies and 3 momenta. So the only thing where I can use Kramers-Kronig and quickly intuitively expect what it happens is basically these flat regions here, but maybe we should think more about it to understand. I mean, the log divergences are already more difficult to connect. But still maybe possible, yeah.
Yeah, I mean, I didn't do it for Chi3. I mean, we know it for Chi1, of course, but
yeah, we use it for Chi1, for Chi3. It exists, but it's less practical to use. I agree.
Okay, thank you very much for the presentation. Thanks.
Thank you for the question.
Okay.
May I ask a question?
Sure, Sergey.
Could we come to the pre-last slide? The next one, I guess.
This one?
No, next one, please.
Next one.
Yeah. Well, it was pre-last slide in which we were discussing this new type of soliton. Yeah, like that one.
Yes. Yeah.
So, as far as I understand, so that unusual shape is a result of topological structure, right? Of Fermi surface.
Basically, you have this dimerization, and you have to
Yeah, my question is, can you do the opposite conclusion? For example, observing the specific shape of such solitons, can you restore the feature of topological structure?
Can you repeat the question? I'm not sure I understand.
I ask if you observe some macroscopic properties of such solitons, spectrum or whatever, can you restore the topological features, topological properties of the Fermi surface? Can you make like an inverse problem?
So that if I can measure something that tells me that I have a topological well, I would say in experiments, these topological solitons, not in quantum optics, but in polyacetylene-like materials, have been demonstrated, if you want, experimentally, by actually measuring the fact that you have a transmission or you have excitations at a frequency which is actually half of the gap of your insulator. So they know the gap, but they go excited and they see there is the response at mid-gap. If there is spectral density there, then you start thinking, oh, then I have something as some kind of domain wall, which is then necessarily topological because it connects to different dimerizations. So this is how in experiment they measure it. So in using optics, it could be very easily, because if it's already hybridized with your photons, then you do transmission, or you can do pump probe, and you see surely something which is excitable. You see spectral weight inside the gap of your. So this is a good signature. And also the experiments are in solid state in polyacetylene. They put extra particles and they see how they generate, because every particle, if you put an extra electron, it should be accommodated in these domain walls, and the more electrons you put, the more domain walls you can form. And so you can also see in solid state, they can also, I guess, some way image this as well. You have these arrays of tubes in 1D, and they can see how these domain walls interact across tubes. So they can do several things which can also be copied here, let's say. But I have not say this is very interesting, because, for instance, I think that I don't know is that in optics you have this noise from, if you couple it to a cavity, you have noise from the loss of the cavity. And it would be interesting to see how robust these solitons are to this noise from the cavity, for instance, because if I hybridize them with photons, then I will, because they can move like quasi-particles, but if I have noise, and typically if the strength of the noise is smaller than the gap, they should be robust, but the noise from the cavity is very non-local, because the photons are very delocalized. So one should analyze this, and one should write equations to study this, some kind of algebra equation for the motion of these solitons. This is also on our list, but the strength is limited. Like we can do a limited number of things.
Thank you so much.
Okay, thank you very much for this presentation and the answers.